Good afternoon to everyone, and welcome to a new online event within the EMS Webinar series. In this occasion, we present some aspects of a topic which appear frequently and recurrently in the media. The topic is cloud observation and even its possible modification. We expect that it is of your interest. Before introducing our speaker today, let me recall some practical hints. The webinar is being recorded and will be published later on the EMS YouTube channel. Please use only the chat to write your question. This is the only way to ask questions. All these questions will be answered at the end of the presentation. Vesna Juricic will organize and group and read the questions on the chat. Please send your proposals and suggestions for topics and speakers to us. Whatever topic you consider could be of interest, I'm sure it would fit in this format. And now, let me introduce to our invited speaker today, José Luis Sánchez Gómez. He's full professor at the University of León in Spain. He has been teaching more than 40 years and researching in the field of atmospheric science. He was also editor-in-chief of one journal, Atmospheric Research, during 10 years, has tutorized many doctoral theses and published a big number of papers in international journals. The title of his today presentation, as you can see in the slide, is Aerial Research Platforms. What processes can be seen inside clouds? Please, José Luis, go ahead with your presentation.
Okay, thank you for the introduction, and thank you for the invitation to EMS. And well, I will try to present this webinar about some processes that occur inside clouds. And we are talking about clouds. The first question is, why are important clouds? By many reasons, but we need to think in the planet. And in the planet is possible. Clouds contain water and therefore are involved in the water cycle. They also have is important or are important in the radiance and the radiation balance, and they contribute to making ecosystem and life in general terms to be feasible of this planet. The first question is how is possible to observe clouds? Obviously we can use different techniques, instruments, for instance, satellite. We have many types of satellites, many types of radiometers and other instruments. And can be used. Good, this is good. The other possibility is to use meteorological radar. This is our radar. This is a C-band radar, and with the C-band radar we obtain images in terms of reflectivity, and reflectivity has a relationship with intensity of precipitation, and it's possible to obtain with radars, many radar variables, and to work with these databases. The other possibility is to use on the left corner. We can see we use, for instance, ceilometers or multi-channel microarray radiometer. That this is very interesting. Other types of radar, in this case, is a micro radar. Well, and the other possibility is to use a visibilimeter in order to know, obviously, the visibility, but this type of visibilimeter. With this type of visibilimeter, we analyze the intensity of precipitation, and we can discriminate between, for instance, snow or hail or intense or drizzle, for instance, rain. But the question that we have is, when a cloud or why a cloud is starting to produce rain or hail or snow. With this instrumentation, is possible, yes, but well, we need a little more. We need to know in detail everything that happens inside them. WMO has an atlas, very interesting, based on pictures, and is well, they are marvelous pictures. In our association, we have a competition, and the AME, in the Spanish Meteorological Association. The name of our competition is Photo Meteor, and this is the web page. And I invite to visit our web page, because it's well, you can find extremely good, very good, very impressive pictures of different clouds. But well, this webinar is focused in order to know what's happening inside, and we were talking about the research. First of all, what's happened when we are comparing the saturated water vapor upon a droplet and a sphere, and we compare to over a flat surface. Well, it's different, and it's different because the surface tension is different. To overcome surface tension, it is necessary to heat the surface with the greatest number of water molecules. It is necessary to increase the vapor concentration. Right. Well, we assume that we have now we have a fact that the heterogeneous nucleation has occurred, and why? Normally, droplets in the beginning has been formed because a vapor is formed by nucleation or with the help of CCN, transforming the vapor in water, in liquid water, in a droplet. CCN is an aerosol with the capacity to nucleate water from the vapor, and this and we have many. The concentration of CCN is very high. Normally, we have tens of thousands of CCN per cubic centimeter in the environment. It is to say, we have many possibilities to have CCN. We assume that we have a first droplet. The radius usually is about 1 micron or less, even smaller. We see the curve. This curve represents the color equation. What is the color equation? Is representing the equilibrium condition humidity with the aqueous solution droplets for different radius. In this figure, we see in the vertical axis the saturation ratio between the saturation considering the a droplet and for flat surface. This is the saturation ratio, and in the horizontal axis we have the drop radius for different radius. We suppose for instance, that the environment is like something, and we are in the A point. The A point means that it was necessary to form a droplet if we found a saturation ratio of 1.002. But this is very small. And in the beginning, the growth is by vapor diffusion, obviously. And when we have inside clouds in the beginning, or we will have droplets about 3 microns, 4 microns, maybe 15 microns. But in order to have precipitation drops, we need to grow, and at least the final radio, the final diameter will be 200 microns at least. And in this case, we will have some possibilities to have rain on the ground. But we began with position A. A is with a saturation of 1.002. And we need to cross to this part, and to this part we will have maybe 10 microns or something like that. If we would like to pass through this part to this part, it will be necessary to find a cloudy area with a saturation S greater than unity, and well, with a high concentration of vapor. Yeah, this is the reason that, well, sometimes it's possible and sometimes it's not possible, because inside the cloud it's not possible to find this concentration of vapor. What happens if the droplet doesn't grow? Obviously, it has any chance of being able to precipitate. That is obviously. This is the reason that, among others, that we can see clouds, and sometimes it's possible to see that they produce precipitation, in another case, not. Well, we assume that we have the growth vapor, the growth diffusion, right, is working. And well, and what is the next step? The mechanism is starting to be different. Why? Because the diffusion growth dominates during the initial stage of cloud information. But when drops becomes, this mode becomes very slow. Once a drops reaches about 30-40 microns. And we need another mechanism, and the mechanism is that we see in this slide, the coalescence. What is that? Well, what is the scenario that we have? We see in the left part. We see different droplets or drops with different radius. And probably they are moving. And if they are moving, obviously they will have a possibility to be collide. And after the collision, what's happened? Maybe will be possible to form a larger drop or not. This is we are talking about the coalescence. It is to say, we have a collision. We need to talk about the collision efficiency. And the collision efficiency will be a relationship between the impact area according to aerodynamic effect. Maybe we have some or not. It's a probability. And the second thing, as after the collision, maybe we have coalescence, and the efficiency of the coalescence efficiency is the probability to form a large drops. This is well, is possible to find in the many references or some reference about the probability to form a large depending of different sizes that they are impacting. And most of experiments were made in wind tunnel. Finally, we have a particle size distribution, and the next step is, well, we are forming raindrops, but large raindrops maybe be subject to hydrodynamic instability maybe they make to break up into smaller drops, and therefore is changing and changing and changing the particle distribution. This is more or less is here in this part of the slide, right? Thinking in the mechanism, thinking in everything. It is something like this, right? In the beginning, we need to have an area in order to try to exceed the critical radius. The second state is, okay, we find this region, but the second thing is to need to have collision and collision. And for that, the cloud volume must be sufficient in order to collide. And the third stage is the collision and the coalescence processes must be as efficient as possible. And finally, we will have or not, we will have rain. This is difficult. Another possibility: we are in a part we are in a region of our cloud that the temperature is -5 or -10 or something like that. It is to say, under is less 0 degrees. What's happened in this case? We need to form an ice crystal, but ice crystal is not easy to find inside the cloud by some reason. But the first reason is we need the help of ice nuclei. Ice nuclei is an aerosol. It's not a CCN, completely different. Ice nuclei, the concentration is really very low, and they are 4 different modes for ice nucleation. It is represented here in this slide. These are representing the ice nuclei in environment with vapor, and the first mode to produce an ice crystal is deposition of water vapor, the first mode. The second mode is condensation, freezing nuclei. It is to say, first of all, the ice nuclei serves like a CCN, and after immediately produce an ice crystal, the nucleation occurs. The third is by immersion nuclei, freezing the droplet and the ice nuclei immerse before is the nucleation. And the last is by contact nuclei. Has an impact, and finally is producing or is forming an ice crystal. But the concentration of ice nuclei is very low. It's completely different than the convective, the CCN. We have in this table some experiments. We were measuring in our cloud chamber different ice nuclei in different areas in Spain and in France. They are very similar. The median ice nuclei activated per liter and -15 is normally is about 7, but the standard deviation is very high. -19 is about 35 and is increasing depending on the temperature. It is to say, the activation of ice nuclei is depending of the temperature. And we see in this figure the ice crystal in our precipitated in our cloud chamber. Okay, what means? Well, it's clear that our temperature down -10 degrees is very likely to find supercool water droplets and maybe some crystal. An example is a hailstorm. Hailstorm, we have many hailstorms because we have two ways to form a hailstorm. This is one. Is the system or the method is named dry growth. And in the dry growth, as you see in the center, we have supercool liquid water, and in the skin we have ice. This is an example of the importance to understand and to know what is the mechanism to produce supercool liquid water, and to understand and try to understand what is the system to produce crystal or to freeze all supercool liquid water. Supercool liquid water is very, very important. Well, we assume now that we have in a region inside of our cloud, we have droplets or drops, sorry. We have drops, we have obviously vapor, and we have an ice crystal. And well, one moment. Wow. And we see what is starting. Well, what's happened? The saturation vapor pressure in front of a liquid droplet or liquid drop is higher than in front of a crystal. What is the result? The result is clear. The result will be the droplets will tend to reduce, to evaporate, to reduce the size, and the crystal will tend to grow. But this is clear. This is the phenomenon named Bergeron-Findeisen, and is very, very known from many years. Okay, in another region. Okay, we have drops, supercool liquid water, supercool liquid drops. We have an ice crystal growing, and continue. The ice crystal will be continue growing. The ice crystal growth by accretion. This is the name. It is to say rhyming. And well, we see this is the sorry. Oof. Sorry. Okay. And this is that occur. Well, now summarizing, what is the type of mechanism? What is the type of processes that we have inside clouds? This is an schematic that is containing all types of processes. If someone is interested to see and to read, we have a paper published in the Atmospheric Research indicating the schematic of CCN, vapor, ice nuclei, forming cloud droplets, growing in order to form raindrops or ice crystal, to form a solid aggregate, and finally the different types of precipitation. Well, and finally, now we are inside. We need to know what's happened inside by experimental campaigns. We use in Spain, we use a platform, aerial platform by INTA, and the first thing is it is necessary to have a good platform because well, flights is very, very complicated. And you need to think that the second thing is you need to understand that you will need to fly at night or okay, during sunny days or no sunny days with cloudy days. Well, it's not easy, and it's very important to have expert pilots. In all cases, the videos were provided by our project in the past that we were developing and working in Mendoza, in Argentina. Well, now we assume that it's necessary to prepare a campaign. Sorry, I think I will stop. Right. And now, and it's not easy. Believe me, it's not easy. It's necessary to prepare many aspects. Many people are involved to prepare the campaigns. It's necessary to have training, to develop models. You see in the left part the result of our campaign in storms inside rainstorm and hailstorm, and you can see the damage caused by the fuselage. Obviously, you need a good instrumentation. We use this type of instrumentation. It's really very good. This is the platform that we were using during many years. This is the 4 people that were of my team that were involved directly on the campaign. That's me. This is the new platform, a property of INTA, Instituto Nacional de Técnica Aeroespacial in Spain. This is the airport in the CR, an airport specializing for test flights. And well, it's not easy to prepare, believe me. And well, finally, you need to fly, right? As this is in a convection, this is an cumulus nimbus. As you see, the goal is to try to have what's happening inside, but we need to try to surf the clouds and enter when the entry is and the exit is well defined, especially when the exit is well defined. You see in the windshield the supercool liquid water because freeze in the windshield. This is one problem that we have, and it's necessary to take to have in mind this. Well, in a campaign, we're in a campaign. We are testing the different models, and this is the test flight, and the plane is following a track in different moments, and different regions. The platform and obviously the people that are inside, the team that they are inside, we are taking data and analyzing the type of hydrometeors that we are finding. We can classify in different. This is the view with instrumentation, and we see that in some region it's possible to have cloud droplets, in another region large droplet, in another supercool grapple, needles, or another types of crystal. It's interesting because when you are finding supercool large droplets, maybe you find a grapple, but likely you will find only supercool large droplets, right? And this is the ingredient in order to have problem for icing aircraft, for instance. Finally, we have a video to see. We were analyzing the best trajectory in order. In this case, the goal was to find to analyze and to find supercool liquid drops with this instrument and with this platform. I think this can be seen on the leading edge of the wind profile, the ice, the icing the craft is formed. You see. Well, this platform has the icing system, but the icing system is not perfect. You see, the icing is formed, the turbulence is really high. Now, icing aircraft is formed. The supercool liquid water. Supercool liquid water, necessary to think that they are at -10, -15 degrees in a metastable. And when we produce an impact, immediately freezes. Well, and everything for what? to have good models in order to forecast where is the area, where is the temperature that we'll have, agua por agua in different tracks. We have 2 models. The models were obviously validated and calibrated in different conditions with this type of campaign. And well, if someone wants to see more references, you can find in the right part of our slide, of the slide, the different papers of different books. Okay, no more in 30 minutes.
Okay, thank you very much, José Luis. And now we pass to the questions. Please, Vesna, go ahead with the questions.
Yeah, first question is actually from you, Ernesto. Could you comment on the current status of clouds modification science? Which are the main uncertainties and challenges in quantifying the effect of our intervention in clouds?
Depending of cloud. Okay, there are many types of clouds in many different processes, and it's really very complicated. What is my experience? I was working in weather modification. It's 42 years or something like that. And in some cases, the system, in order to seed with ice nuclei, in order to have more hail embryos, is working. And in other cases, it's not possible. The effect is not possible. We have in Spain and in France, in other countries, we have different networks of hail paths. Hail path is a system to analyze the sizes of different hail precipitated, and sometimes it's possible that the success was, well, more or less good, but we don't have the magic tool in order to know perfectly what is the system to avoid hail or to increase precipitation. We need to have experiment. And in my case, and I believe that if we have weather modification experiments, we will need in all cases research. The system is working, maybe it's working in some cases, but in another not. Following the American Society of Civil Engineers, that they were working analyzing the different types of weather modification, well, they find that probably the benefit is really high, but in other cases of weather modification, for instance, snowpack, I am completely certain that is working, but you need to find a specific situation, and the number of this specific situation probably in a winter is very slow. But if you have everything ready in order to operate in the moment that you have this condition, probably you will have success. But if not, it's nothing, absolutely nothing. We know perfectly that it's impossible to disappear clouds. This is well, absolutely impossible. Maybe it will be possible to increase the precipitation, but depending on types of clouds, depending.
Okay. Branko Grisogono says, splendid work, thank you. My professor of cloud physics, John Hallett, would enjoy it. What are results when air flows through these icy systems at low, medium, or high speeds?
Sorry, who is? Welcome.
Branko Grisogono.
Could you come in on class? Thank you, Mr. Pro Cloud Physics. Okay. Enjoy. Okay. Yes. The icy system. Good. Very good. Very good question. Now we have we know that by Airbus that they are changing the icing and anti-icing system in planes. That means that maybe it doesn't work. They actually doesn't work in all cases. Well, we have many databases with liquid water content and with our platform with another system in order to detect where is the icing aircraft. And we found that with the liquid water, with the concentration of 1 gram per cubic meter, it's possible to have icing aircraft. This is for aircraft, but the icing aircraft, depending of type of platforms, is not the same. The plane of 212 than the other 295, or to use the icing or anti-icing system. The other thing is the unmanned aerial vehicle. The system needs to be developed because, well, it's the key point and it's a weak point in the development of drones. And we are working all together with the INTA in order to increase our knowledge and to have another systems and another instrument to avoid icing and to de-icing or to anti-icing system. But this is an open question at this moment.
We have another one from Aminu Bello. Hi, good day to you all. I'm Aminu Ahmed from Nigeria and a graduate student from the University of Maiduguri, Borno State, Nigeria. And I have obtained BC Geography and now a Master in Hydrology in view. And there is actually no question. Just introducing himself.
Continue with the other question. We flew in an area with ground generators, silver iodide generators running, and we flew before to be on this area, and we were analyzing what is the concentration of ice crystal before to enter in this area, and when we were exactly in the vertical of this area. Completely different, absolutely completely different. Pilots doesn't understand and doesn't know about the weather modification, but when we flew, they told me what's happened. Clouds were changing completely. But this is very different to demonstrate that the silver iodide, the ice nuclei, was responsible to create the ice crystal or not, because we have the problem is we have no exactly two clouds exactly one and another exactly the same. And if we have two clouds exactly the same, we will have the possibility to have experiment in one and to compare with another one. It's not possible and it's difficult. But we found some evidence that in some cases, in system, very clear, in some cases is working, and probably the benefit is better than the cost. But to me, very clear. And for the American Society of Civil Engineers, they told me that absolutely clear. But we need to research many aspects. If we don't understand what's happening inside exactly, we don't know exactly what's happening inside of clouds, will be very difficult to find to have a conclusion that the success and the system is working perfect. It's maybe in 40 years.
Yeah, this corresponds to Ernesto's comments. From your presentation, we may draw the conclusion that this field still needs a lot of research to reach a mature level. Is that right?
Yeah, yeah. We need a lot of research, exactly, to reach a mature level. Yeah, absolutely, absolutely. Well, research is changing. Research studies. Now everybody is working in climate change. You will have thousands and thousands of teams working in climate change. And in meteorology, less. And in cloud physics, it's expensive and it's difficult. In Europe, we have a good possibility. We have, in my opinion, we need by many reasons. But the other, for instance, the companies, Airbus or another companies developing planes, they need to know exactly in detail what's happening inside, because they will need to create rules, policies to fly in severe weather. And we know that severe weather is increasing the number of situations that we have. To me, it's absolutely clear.
There is another one from Ernesto. Can you comment on the general quality of the work of consultants and commercial enterprises developing activity in this field, trying to apply the current knowledge to enhance precipitation or suppress hail, aiming at the agricultural sector?
Yeah. I know, for instance, I know some project in developing in Spain, in Aragon, in Madrid, or in South France. And if they follow a scientific system, and they need at least 20 years, 20 years with research, probably they will have a good result. No perfect result, but good result. It is to say, maybe they can, with using, for instance, hail pads, they will find that can be reduced the kinetic energy about 20, 30%. That is probably, but no, never 100%. But yes, 30%, 30%, 20%, 40% is fine. It's fine. This is reducing the damage, probably an important number. Is possible to use in all cases the same system of hail suppression? No, completely different. I was preparing a project designing a project in Argentina, and in Argentina the system used is by planes. In Europe, to me, in Spain and in France, the aerial traffic is terrible, and we were using this system in Spain with aerial platforms, and seeding with aerial platform in Spain, and it was impossible because when you decide to go with your plane in order to seed, probably it's too late, because you need to arrive. There are many aerial traffic controls, normal, and well, it's very, very difficult. But in Argentina, perfect. In South France, they have a hail suppression system, maybe about, I don't remember exactly, but I think it's about 75 years or something like that. It's impossible to have a project during 75 years if you are not working seriously, working with research, working with sharing your knowledge with agricultures, with authorities, is okay. But never, weather modification is not a laundry that you put in on and it's working, you put in off, is not working. No. It's more complicated, and you will need always, in all cases, to increase your knowledge about the processes and the mechanisms inside of clouds, and in order to know what is the precipitation and why you have a precipitation like hail or like or rain or something like that, because finally you will need to demonstrate that you have positive result. Emirates, United Emirates, for instance, has very good prices in order to increase the knowledge, and I think it's a good idea. But well, there are another priorities in Europe, and I don't understand. Climate change is okay, I understand, but cloud is cloud, and cloud is inside of the water cycle. A water cycle is very important for us and for the planet.
Thank you. Amino Bello Ahmed asks, why is the Arabian Sea experiencing cyclones?
I was in the past analyzing a project in order to increase the rain in Emirates. Well, the area is very difficult, and I know another project developed by NCAR or USA companies. The problem is you are spending a lot of money. Finally, you have maybe in a campaign 2, 3, 4 days with a good situation, meteorological situation, in order to have your experiment. And well, it's not the same. It's not the good area. You need to increase fast. You increase fast your knowledge. But it's interesting. It's interesting. I don't remember at this time. I know just a little some projects, a small project or some proposal of projects presented to Emirates, Arab Emirates, and well, it's interesting. But we need to increase. Another country is Russia. Russia. They are my friends are working Upshive, and they have very good experiment. In Bulgaria, they have good experiments. In Greece, in Spain, something. In Europe, always is hail suppression. In Russia, I think it's hail suppression, but I don't really know exactly. In South America, in Chile, they have some project to increase the precipitation because they have many problems. And well, in India is nice. They are working in weather modification for rain enhancement at least, I think it's 15 years or something like that. I don't remember because time is running very fast. And another countries. Well, this is my experience. This is my obviously in Canada and in North USA, in North USA, in North Dakota, and I know this project because I was in the past in the project. They have very good experiment in Canada, in Alberta. The hail suppression project is paid by the assurance company in order to reduce the damage caused in building, not agriculture, building, and the assurance company, they are paying, right? And I don't know how many years they are working in this project, but maybe 50 years. Nobody is paying money for nothing. Clear. But we need to increase our knowledge always.
Okay. Thank you very much. Let me thank all for your attendance, and a special thanks to our today's invited speaker, José Luis Sánchez.
Thank you.
The next 2 webinars are scheduled for the 9th and the 16th of April. The first one will be devoted to the EMS journey to net zero emissions. and will be delivered by the president of EMS, Liz Bentley. The second one will be about the rapidly attributing extreme weather events to climate change, and will be delivered by Freddy Otto and Ben Clark from the World Weather Attribution Initiative. Thank you all, and I hope to see you again at our next EMS webinars. Thank you.
Thank you very much for all.